So now time for some exercises. So give an example of a set X which is non-empty and a monotone class M on X such that X empty set belong to M and M is not a sigma algebra. So we saw in many cases if you have a monotone class very often it becomes, which is an algebra, then generated by an algebra, then it is the same as a sigma algebra. So we are wanting a monotone class which is not a sigma algebra, and so solution. So let us take X equal to N and M to be the empty set X union AN, N equals 1, 2, 3, etc., where AN is the set 1, 2 up to N. So this is not a sigma algebra, since if N is bigger than M, we have AN minus AM is equal to M plus 1 up to N, which does not belong to M, and therefore it is not closed under differences, so this is not a sigma algebra. And it is a monotone class because if you take EI increasing in M, then if X equals one of the EI, we already have that union EI equal to X belongs to M. If X is not in equal to any EI for all I, then you have union EI is AM, where M is the max of the I's, because you have. Similarly, if you have intersection EI decreasing, then if phi equal to an EI, then the intersection EI equal to phi. Otherwise, if phi is not any EI, then intersection EI will be the minimum, will be AM, M equals minimum. There will be a minimum in this case. You can't have a superinf because in this case you have this. Okay, so here we put or X, it could be X also. Okay, then M is the minimum, and so this is a monotone class, and consequently you have, it's not a sigma algebra. 2. F and G integrable over Rn, and then show that A F star G equals G star F, and B F star G star H equals F star G star H, where FGH integrable over R. Okay. Now, in this case, F star G is integrable if F and G is integrable and H is integrable, so the convolution is defined. Similarly, G star H is integrable and therefore F star G star H is also integrable. So everything is well defined. So this is just a question of Fubini's theorem and translation invariance. So F star G of X equals integral over Rn F of X minus Y Gy dmny. Now if I put x minus y equal to z, and then you have y equals x minus z. Okay, and then we have seen this exercise already. When you make a translation in Rn, then the integral just behaves like the usual substitution law, and therefore this becomes f of z and g of x minus z dmn z, and that's equal to g star f at x. Okay, we have seen that if you translate a function and then integrate, it just integrates over the translated domain. But here we are integrating over Rn, and therefore the translated domain is the same. Okay, B. So f star g star h at x, this is equal to integral on Rn f star g at x minus y into h of y dmn y, which is equal to integral over Rn of f of x minus y minus t g of t h of y dmn t dmn y. Now since fgh integrable, integral Rn mod f of x minus y minus t gt h mod hy dmn t dmn y is finite. We have checked it many times. Translation invariance matters, and therefore Fubini applies. Fubini can be applied. So f star g star h of x is equal to integral Rn now I'll bring out g of t because it doesn't seem to. So I'm going to integrate first with respect to y, right? So you have f of x minus y integral Rn f of x minus y minus t h of y dmn y dmn t. Now you put x minus y minus t equal to z, and then y equals x minus t minus z, and therefore this becomes integral Rn g of t integral over Rn, the same as we did for the commutativity. So x minus y minus t is f of z, and then h of x minus t minus z dmn z dmn t. Once again we apply Fubini. So again Fubini integral Rn f of z I bring out, and then integral over Rn h of x minus t minus z g of t, and then dmn t dmn z. Now this integral here, so that's equal to integral over Rn f of z g star h at x minus z dmn z, and that's now equal to f star g star h evaluated at x. Okay, because whether it is G star H star F or F star G star H, it doesn't matter because of the commutativity we already have. Okay, so that proves 3. Fg integrable on Rn show that F star G hat, that is a Fourier transform, is F hat G hat. This is one of the most important properties of the convolution and Fourier transform. These are used very often in PD analysis, partial differential equations. So you take the convolution product and take the Fourier transform, then it becomes a usual multiplication. Okay, and so F star G hat at any point psi is integral over Rn e power minus 2 pi I x psi, and then F star Gx dmnx, and that's equal to integral over Rn e power minus 2 pi I x dot psi integral over Rn f of x minus y gy dmny dmnx. Again, integral over Rn mod e power minus 2 pi I x dot psi, this equal to 1 mod f of x minus y mod gy dmny dmnx is finite. Again, this is usual, we have done it many times, and therefore Fubini, so Fubini implies f star g hat psi equal to integral Rn gy comes out, and then you have integral over Rn e power minus 2 pi I x dot psi f of x minus y dmnx dmny, and that's equal to integral Rn g of y integral Rn e power minus 2 pi I x minus y dot psi f of x minus y dmnx, and then you put e power minus 2 pi I y psi dmny. Now again, by translation invariance, x minus y, you can change it to some z if you like, and therefore this will become nothing but f star f hat psi. So you can pull it out, so that's equal to f hat psi, and what's inside is nothing but g hat psi, and therefore you have this nice property. So now let us the next exercise is a generalization of the idea. When we do integration, especially if you have a non-negative function, so if I have a function say on 0 1 like this, f is some function like this, then integral f over this interval is nothing but the area under this curve. So it is the area of the set. So we are going to generalize this notion in the next exercise. Okay, so XS measurable space, f x to r measurable and non-negative. You define these superstar f equal to set of all xt in x cross r such that 0 less than equal to t less than equal to f of x. So it is, we are precisely defining this area, and we are including these two portions. And V sub star f equal to set of all xt in x cross r such that 0 less than or equal to t strictly less than f of x. So we are excluding the boundary. Okay, so A, f simple non-negative, then V superstar f, V substar f are measurable on x cross r. We give the usual product topology. So here you have the Lebesgue, the S, and here you have the Lebesgue measure. Okay. So let us take f equals alpha times chi of E, where alpha is greater or equal to 0. Alpha is strictly positive because if it's 0, it's a 0 function and there's nothing for you to do, and E belongs to S. Okay. So then V superstar f is nothing but, so you can take, so E complement cross singleton 0 union, because if you take E complement, f is 0 and therefore t will also have to be forcibly 0. So therefore you have this cross E cross 0 alpha. And then this is measurable rectangles and therefore this is measurable. So this is a measurable rectangle, this is also measurable rectangle. And V substar of f is nothing but E complement cross 0 union E cross 0 open alpha, and again this is measured. Okay, so now let f non-zero, f equals sigma alpha I chi of ei, I equals 1 to n, alpha I positive and ei in S, 1 less than to I less than equal to n. Then V superstar f equal to intersection ei complement cross 0. This is where everything is 0. Union I equals 1 to n ei cross 0 alpha I, and then this is measurable again because it's a union of measurable rectangles. And then V substar of f is the same thing except you have 0 alpha here. Okay, so this is also measurable. B, fg non-negative, fx less than or equal to gx for all x. Then V star f is less than or equal to V star g, and V sub star f is contained in, contained in V sub star g. So let us take xt in V star f. So this means 0 less than or equal to t less than or equal to mod fx, f of x, but that's less than or equal to g of x, and therefore xt belongs to V star g. Similarly, V sub star f is contained in V sub star g. Let fn be greater or equal to 0, and Fn increasing to F. Then V sub star Fn n equals 1 to infinity increases to V sub star F, and if Fn decreases to F, then V superstar Fn decreases to V superstar F. So V substar Fn increasing when Fn increasing follows from B. Similarly, V superstar Fn decreasing when Fn decreases also follows from B. Okay, so let us take xt belonging to union n equals 1 to infinity V sub star Fn. This means what? There exists an n such that 0 less than or equal to t less than or equal to f of xn. But that goes to f of x. So sorry, this is strictly less. That means xt belongs to V star of f. Now if xt belongs to V star of f, then you have that 0 less than or equal to t strictly less than f of x implies there exists an n, since fn increases to f, therefore there exists an n such as 0 less than or equal to t strictly less than fn x which is less than or equal to f of x. You can insert fn because fn converges to f of x and t is strictly less, and therefore this implies that x belongs to V star Fn, which is contained in union n equals 1 to infinity V star m equals 1 Fn. So we have both inclusions here, and therefore you have union V star Fn n equals 1 to infinity equals V star of . Similarly, if xt, so Fn decreasing to f, if xt belongs to intersection n equals 1 to infinity V star of Fn, so 0 less than or equal to t less than or equal to Fn of x for all n, and this implies that 0 less than or equal to t less than or equal to f of x. Okay, so this implies that xt belongs to V superstar f. Conversely, xt belongs to V superstar f, so this means 0 less than or equal to t less than or equal to fx, but fx is less than or equal to fnx for all n, and this implies xt belongs to intersection n equals 1 to V superstar fn, and therefore those two are equal. So we have V superstar f equals V super intersection So D, F non-negative measurable, then V star F, V sub star F measurable. So up to now we are dealing with just doing set theoretic arguments. So now we want to show that these two are measurable. Okay, so F is non-negative measurable, therefore there exists Fn greater or equal to 0, simple, and Fn increases to F. Then Vn, V of substar, Fn measurable, and V substar Fn increases to V star of F, and therefore this implies that V star of F is measurable. Now you let Gn equals f of x plus 1 by n. Then Gn decreases to f. And we know that by preceding argument, V substar Gn is measured. So let xt belong to V star of f. This implies 0 less than or equal to t less than or equal to f of x, which is strictly less than Gn of x for all n. So this implies xt belongs to intersection n equals 1 to infinity V substar Gn. And if xt belongs to intersection V substar Gn n equals 1 to infinity, then 0 less than or equal to t less than Gn of x, which is f of x plus 1 by n, and this implies that 0 less than or equal to t less than or equal to f of x, which is equal to v super. So this implies xt belongs to v superstar of f. So therefore we get V superstar f equals intersection n equals 1 to infinity V substar Gn, and these are all measurable, implies measurable. Then E, x s mu sigma finite measure space, and lambda equals mu cross m1. Then lambda of V substar f equals lambda of V superstar f, which is equal to integral over x f d mu. So this is, you can say, area under the curve. because we saw that picture. So if this is f, then this without the boundary is v sub star, with the boundary it is v superstar, and that lambda measure is what you want. Okay, so lambda is the product measure, and therefore that gives you area under the curve. Okay, so lambda v sub star f, that's a measurable set in the product measure. Okay, so this is equal to, by Fubini's theorem, intersection over x m1 of v sub star f x d mu x. What is v sub star f? This is equal to set of all x t. This is at 0 less than or equal to x t less than equal strictly less than f of x, and that is equal to, so v star f super x, so for any fixed x, so this is nothing but the interval 0 to f of x open. Similarly, v superstar f super x is nothing but 0 to f of x closed. So m1 of this interval, this is equal to integral x f of x d mu x. It's equal to integral x f d mu. Similarly, lambda v superstar f is the same thing. So integral over x f of x d mu x, which is equal to integral f d mu over x. So you see, we have the way the product measure is defined just generalizes the notion of area. Okay, so we will stop with this. So this chapter has ended. Next time we will take up a new chapter. These are called signed measures, where measures need not be necessarily positive.